Welcome to lecture number 7, and we are going to discuss about coordinate transformation, dynamical variable in terms of generalized coordinates and Lagrangian equation. This is what we are going to discuss. We consider n particle and having k holonomic constants. Okay. The position of these n particles, capital N particles, are given as Ri, vector Ri. Okay. We are talking about the degree of freedom n. Okay. Means which is related with the constants, and we are having k constant. So the degree of freedom will be 3n minus k. We are talking about, we are not including the rotational degree of freedom for these particles. Okay, you can treat all these particles as a point particles. So in order to describe, if we are having n degree of freedom, so in order to describe this system, the dynamics of the system, we need n generalized coordinate, which are given as q1, q2, q3, and so on up to qn. To write in more concise form, you can also choose qj to denote generalized coordinate. J ranges from 1 to n. Now, since this vector has in the Cartesian coordinate can be written as xi x cap plus yi y cap plus zi z cap. So this denotes the position of ith particle, and I ranges from 1 to capital N, right? We are having capital N particle. Now, since Q1, Q2 and Qn are describing, and R1, R2 and Rn represent the same physical system, thus one set of coordinate must be function to other set, right? So what I mean to say, this Ri we should be able to describe with some function of Q1, Q2 up to Qn. Similarly, the particle of the position of this one should be written as function of Q1, Q2 up to Qn. So this is the vectorial form, but if I want to write component wise, so xi will be the function of generalized coordinate and time. Here we are defining holonomic constants. It can be rheonomic or scleronomic, and if it is having time dependent, of course, here it is rheonomic and time dependence will come. So that's why here time we are putting. And then this is what xi will be q1 function of generalized coordinate, all n generalized coordinate. Y will be function of all n generalized coordinate. And similarly, zi. This is for the particle I. It might be looking very abstract to you. So let's take one example, our favorite example, pendulum, simple pendulum. And you can write x1 as L sine theta 1, right here. As we said that we have only 1 degree of freedom, so we need only one generalized coordinate. We are choosing the generalized coordinate to be theta 1. x1 we can write L sine theta 1. And this is what exactly I said in this slide, that I can write xi as function of generalized coordinate and time. Here, time is not appearing because it's holonomic, scleronomic constant. This length is fixed. If it was varying with time, then yes, of course. y1 is written as L cos theta 1, and then vector in the vectorial form. If you want to write, this will be like this. Okay. In general, it will be function of theta 1 and time. This is for the two particles. Okay. We are having x1 and y1, x2 and y2. We know that there are 2 degrees of freedom, and then in previous class we chose the generalized coordinate to be theta 1 and theta 2. So we can write this one like this. And what is this? X1 is function, function of theta 1, y1 is also function of theta 1, x2 is function of theta 1 and theta 2, y2 is function of theta 1, theta 2. So in general, R1 and R2 are function of theta 1, and R2 is function of theta 1 and theta 2 and time. So this is what we had written in the previous slide, that in general, the xi coordinate, it can be x1, okay, will be function of generalized coordinate. Okay. Here for the double pendulum, q1 is theta 1, q2 is theta 2. For single pendulum, there is only one generalized coordinate, which is q1 is equal to theta 1. Now, how to write the kinetic energy terms of the generalized coordinates? Well, we know that in the simple Cartesian form, the kinetic energy of the system is half mx dot square plus y dot square plus z dot square. Kinetic energy of the two particles is simply scalar sum of kinetic energy of their individual kinetic energy, sorry. And in the similar manner, if we are having capital N particles, then the total kinetic energy is scalar sum of their individual kinetic energy. So we are having 1 to n particles, and then we can write half mi xi dot square plus yi dot square plus zi dot square. And here I stands for the particle. Okay. We want to write this one, same expression is much more compact form, then we can do so. And in this one, we have to introduce another index for x, y, and z. X I1 means xi1, xi1 means xi, y1 2 means, xi1 is xi, xi2 is yi, xi3 is zi. Okay, and if we introduce this extra index for x, y, and z, of course it should be running from 1 to 3. Here xi dot 1 for xi, 2 for yi, and 3 for zi. Now, how to convert this kinetic energy in the generalized coordinate form? Well, it's not difficult, okay? You know that once you know the xi, which is function of generalized coordinates and time, then you have to do the differentiation. So dxi is partial differentiation of qi, dqn, and so on. And at the end, what you are going to get, differentiation of this with respect to t, del xi by del I and qn dot, this expression you will get. Okay. Okay. And this one you have learned, this one in the slide first lecture. And that's how you can write. So in general, this xi will be sum over j is equal to 1 to n xi mu sum over j. Okay, and you will get this. And you have to simply put this expression for xi here. I am putting same thing, these two sums from here. Half mi is same, and then I'm putting the value of this here, and then I'm squaring it. Well, I mean, it looks complicated, right? This is a scary looking expression, but it is not so. I mean, it's looking like, but in reality, it's not. And in order to understand, let us understand this simple pendulum. And again, we have to find the kinetic energy. So how can you find the kinetic energy? We know that this transformation x is equal to L sine theta, y is equal to L cos theta, x dot if you want to do, you can do dx by d theta, theta dot. Since we are having only one generalized coordinate, so there will be only one term. If there were two generalized coordinate, then there should be two terms. But here we are having only one generalized coordinate. So dx by d theta into theta dot is equal to L cos theta theta dot. Y dot is equal to dy by d theta theta dot is equal to minus L sine theta theta dot. And then you put this x dot whole square plus y dot whole square, and then you will find that this is your kinetic energy. Okay. Now potential energy. Okay, how to write the potential energy in terms of generalized coordinate? Well, it's not complicated. You know that potential depends upon the position of the particle. Okay, and that's why it is function of x1, y1, and z1 coordinate. Similarly for nth particle. So once you know the u is function of x1, y1, and so on, and you know that how to, instead of putting x1, you have to put simply q1, because you know what is the form of x1 in terms of q1. So you can simply write u in terms of generalized coordinate. Again, we are going to take this example. What is the potential energy? Potential energy for this object is minus mgy. Here minus sign is coming because I am taking axis, y-axis downwards. We generally take axis, x-axis something like this. But what I have done is I have rotated this by 180 degree. Not 180 degree, but we have flipped this along the x-axis. Okay, so this y-axis is downwards, it's not upward, and that's why here minus sign is coming. Okay, so what is minus mgy? But we know what is y as a function of generalized coordinate. What is our generalized coordinate is theta. X is L sine theta, y is equal to L cos theta. Answer is very simple. In fact, it is simpler as compared to the kinetic energy. Okay, and we can simply write like this. Okay, so what did we learn till now? We learned in the first lecture basic rules of partial differentiation, and then we learned the different coordinate systems. For example, Cartesian, planar, cylindrical in the third class. Then we discussed about potential, conservative forces, and hence potential, constant motion, degree of freedom, and how the constants guide you to choose the generalized coordinates, right? Expressing physical quantity in terms of generalized coordinate using coordinate transformation relation. Now, let's do a recap of Newtonian mechanics and give the motivation for the Lagrangian mechanics. Okay. I had given this glimpse in the first class itself, but not so rigorously. But let's go in a little bit in more detail. And what is that? In the Newtonian mechanics, if an external force F is applied on an unconstant particle of mass m, then the dynamics of the particle is governed by Newton's equation. And that equation is given as this: F is equal to ma. Okay. Now, if the particle is under constant, then how to incorporate the constant condition in the analysis? In that case, Newton formalism takes into account constants by incorporating an additional force together with external force, and constant force is the representative of the given constant. So if there is a constant, then we have to include one extra force which balances the acceleration and avoids the acceleration in that direction. Okay, it will be clear here. For example, if we say that this is fixed, this is the constant, that length of the string is fixed, then instead of incorporating the constant condition, we introduce constant force, tension in the string. So gravity is pulling this side, but we have to make sure that there is extra tension, extra force, which is called constant force, which is called tension in the string, is balancing in opposite direction to avoid the increase in the length or any kind of acceleration in this direction. Okay, that's what you have done. So constant force must be incorporated in Newton equation, and then you have to write like this. So m dv by dt is equal to mgy plus t in the vector form. Probably you have done this one in the component wise, but if you write this one in the vector form, it is like this. And here we are introducing a new force, and that is the tension, which we don't know. Which is, of course, we know, you can say that it's mg mg cos theta, but but anyways, we have to introduce new constant forces. Okay. For example, here there is another example where we have to introduce this tension in the string, and then to make sure that length is remains same, and then there is no acceleration. There is constant, and then there is no increase in the length of this. Okay. Another is that we have to introduce one more normal force, which will be normal to this surface. So we are having two constants here, two constant forces. If this object is moving on the sliding on the spiral, then this direction of these forces are continuously changing, right? Because it will be normal to the surface and it will keep on changing. Now we are having three pendulums. We have so many constant forces, T1, T2, T3. You have to track all these constant forces. You have to track all these tensor. So what is drawback? I'm not saying that Newtonian mechanics is wrong, but we are saying that kind of demerit with Newtonian mechanics is we have to. One of the demerit is, first of all, this is in vectorial form. You have to keep track of all the components. Okay. And then we have to know the constant forces to handle this Newton's second law. And handling too many constant forces and their components for a system of the particle is really complicated. So general difficulty with this is what we have, and we have also pointed out, which is not so major, that in the form of the forces changes with the coordinate system, and then you see that, which we have already discussed, that in the Cartesian coordinate, the form of this acceleration is like this, form of this acceleration is like this, and spherical it is changing. And so now, new recipe alternative to Newton's law, our life would be really easier if there would exist any new recipe alternative to Newton's law, which does not require to consider constant forces, and also which is not based upon the force and hence the direction. The new recipe should be in the scalar format, not in the vector format. And answer is yes, we have new recipe, and that's called Lagrangian mechanics. Lagrangian formalism, which was formulated by Lagrange, mathematician and astronomer, in 1780 and so on. And what is that recipe? Okay, we introduce new function, and that's called generalized coordinate and generalized velocity and time. That's how we introduce a new quantity which is called Lagrangian of the system, which is function of coordinate and the velocity. All these coordinates are independent. Of course, that is the definition of the generalized coordinate, that they have to be independent, and also these velocities are independent with the coordinate. So for example, q1 and q1 dot are independent coordinate. Position and velocity are not dependent, they are independent, by the way, and this must be shocking to you for if you are hearing for first time, but we can discuss. Okay, the reason for this independence comes from that initial condition. If you want to give for any position, you can give any initial velocity. Okay, after if you give some specify the initial velocity, of course there is going to be there'll be form, the velocity will depend upon x, but initial condition, the velocity and position are independent. At any position you can give any velocity. Okay, so the Lagrangian is defined as this, okay, which is kinetic energy of the system minus the potential energy. And then this kinetic energy should be written in terms of the generalized coordinates and potential energy also. So here, this, since it is all energy, the Lagrangian is scalar, it is not vector. And what is that Lagrangian satisfy? The Lagrange equation is, we do the partial derivative. If you want to know the equation of motion for qj coordinate, qj generalized coordinate, you have to do del L by del qj dot. It means that you have to take the partial derivative of this with respect to qj dot, and then you have to take the total differentiation of this object minus the partial derivative of this minus qj is going to give us 0. That's fine. To define the Lagrangian potential, U should be defined, and this is only true for the conservative force. Okay, you know that only for conservative forces we can write the potential. The advantage of this Lagrangian formalism is we don't have to introduce constant forces, we don't have to track the direction of the forces and so on. And we are going to take our simplest example, that is the pendulum. Okay, so how are you going to handle the pendulum here? Okay, so we know that we have 1 degree of freedom. We know that generalized coordinate can be theta here. We are taking 1, that is theta. And what is x is L sine theta, y is equal to L cos theta. Then we write the kinetic energy as half mx dot square plus y dot square. Potential energy is minus mgy, minus sign is coming because we are defining the axis like this and origin to be here. Then x dot is L cos theta, theta dot, y dot is equal to L sine theta, theta dot here. X dot, L is constant. Sine theta you are going to differentiate with respect to theta and then theta dot. Similarly for y. Then we can write the kinetic energy. We can write the potential energy. We can write the Lagrangian. And then I hope it is clear up to here. We have not done anything great here. Just writing the kinetic energy minus potential energy. Then we are going to write down the Lagrangian equation. So what are we going to do so? How are we going to do so? So we are going to do the differentiation with respect to theta dot. Okay, here. So half is constant, m is constant, L is constant. So if you are going to do the partial differentiation with respect to theta, it will become 2 theta. 2 to cancel, ml square. Theta dot will be coming. And here I am going to do the partial differentiation with respect to theta. Okay. And that's how it is going to come. Minus here sign and minus is here. So it becomes plus. Now the total derivative ml square theta double dot here and then mg sine theta. This is the equation of motion. After that, you can approximate sine theta to be very small and approximate sine theta to be theta. But this is the basic thing which you have derived without considering any direction of the force, without considering any kind of constant force. We take another example where we are having 2 particles, okay, and this particle is sliding here on this surface, and there is 1 pendulum attached to this particle. Now, how are we going to handle using Lagrangian equation? First of all, you can identify all the constants and so on. That's fine. Here are the constants. That this motion is in xy plane. Z1 is 0, Z2 is 0. Y2 has x2 tan alpha because it is sliding on this. And then there is the length of this. This is constant, right? This is what we have. So we have 1, 2, 3, 4 constants. So there are 2 degrees of freedom. If you want to think in terms of subtraction of total particle 2 into n minus number of constants, or if you want to go directly, see there is only one possibility. This will slide this way and then this can oscillate like this. So there are 2 degrees of freedom. This is what I have said just now. So there are 2 degrees of freedom. This can move on this and this can rotate. Now you choose the generalized coordinate. I'm choosing the generalized coordinate and then I'm defining the origin here and then axis I'm defining like this. Right? So S and theta are the generalized coordinate. You can define other coordinate system also, as we discussed in the previous class, that you can have different generalized coordinate, not a problem. But the total number of generalized coordinates should be 10. What is x2? X2 is the x position of this particle. So this is alpha, this is alpha. So x2 is equal to s cos alpha. Y2 is s sin alpha. Okay, don't think minus sign because here y is in this direction. You are free to choose this axis upward. Okay, then you have to choose minus sign there. But anyways, and then x1 is how much? The position of this, the x distance of this, and then from here to here, then you will find that x1 is equal to s cos alpha plus L sin theta, and y1 is equal to s sin alpha plus L cos theta. Now we have to find the kinetic energy. It's easy to find the kinetic energy for S2, particle 2. Here x2 dot, S is cos alpha is constant, so x2 dot is equal to s dot cos alpha, y2 dot is equal to s dot sin alpha. So your kinetic energy for this one is easy. Here x1 is equal to x1 dot minus s dot cos alpha plus L cos theta theta dot. Y1 dot is equal to s dot sin alpha minus L sin theta theta dot. This is what we have done here, and then we have to basically find the kinetic energy by summing all these, and then you will end up with this minus. We have to do the kinetic and potential energy, and then you will end up with this. Now, once you have the kinetic energy and you have the potential energy, we will discuss how to get the equation of motion. So that's all for the class, and we can open for the question.